Okay, so I see my Zoom icon is jumping around, so I'm afraid it's gonna do something that I don't want it to do. Hopefully not. But if I get disconnected again, that's probably what's going on. Okay, sorry for the technical issues. So we're going to basically today finish our exercise of validating the yield spatial temporal stability classes. And we're gonna have time, I believe, to start a new exercise, which is gonna be to create management zones. So I'm really excited about that. I think it's a really cool exercise for us to go through. All right, so let me on my side here go ahead and launch the project that we were working with. So that is the stability validation. Later. All right. So as I just relaunched my script, there's going to be a lot of stuff, or I mean, my environment is empty, so there's going to be a lot of chunks that I'm going to have to run just to catch up. And I think we stopped here. Is that right? Yeah. Okay, so I'm going to come to this chunk here, which is if you're looking at the outline, is the box plots and letter chunk. I'm just going to run all above. If you did not leave any lingering errors in your code, it should work correctly to create all the objects until where we were. So I'm just gonna hold a second here for that to go through. And then let's see. Hmm. I think I had an issue potentially. Let me see here. So this, okay, so this worked. So what is going on? Maybe this one didn't run. Okay, so now should go. All right. So this is where we stopped, and this is where we had ran all the ANOVAs. So again, if you're taking my other class, perhaps this code here makes more sense. If you're not taking my other class, then don't worry about it. I just wanted us to be able to create the ANOVAs and to get the lattice separation for those box plots and really be able to make the following interpretations, right? Or being able to interpret this from a statistical standpoint rather than just looking at the box plots and guessing what was going on. So what I want you all to do, and if you have if you're in a lab that you have a person that you can work with, you can pair up. And if you're by yourself, then I guess you're gonna have to do by yourself. But what I want you to do is come here and basically fill in this text to tell me like, so hi, for example, we can do the first one together, and then I'll let you work on the other ones. So high stable areas have. So when it comes to elevation, we would come here. High stable is the orange one. So it has the highest elevation, right? Is the A. There's no other cell that has A, meaning that, well, I'm assuming you all are familiar with this because this is pretty common in science. So I would assume you probably already learned this in the previous class. But the way we use these letters is if two box plots share at least one letter, it means that those two box plots are not different from each other statistically. For example, here on the elevation, everything is different because all the letters are different. But if we go on slope, for example, we see that the highest slope was medium stable, and then we had the second highest was low stable, And then we see that both high stable and unstable were statistically the same because they share one letter, which is the letter C in this case. So that's how I want you to interpret this is I want you to put into words what is your understanding of how high stable areas are described when it comes to elevation, slope, aspect, ECA, shallow, and deep. So I want you basically, if we do that for the high stable first. So we would go on the elevation plot. It has the highest elevation, right? So high stable areas have elevation highest. And then we can do that for slope. So slope is one of the lowest, right? So the lowest here would be anything that has a C. So high stable has a C. So lowest slope. When it comes to aspect, it has the highest aspect by itself, is not sharing that with anyone. So highest aspect. When it comes to ECA shallow, it's not, so it's B, right? So it's not the highest, but it's also not the lowest. So it's intermediate or medium, perhaps intermediate ECA shallow. And then ECA deep is the highest. It has an A there, right? So highest. Okay, so I want you to do on your side individually for low and unstable and write down your answers here. You can, I mean, perhaps on your side, your letters may be a little bit different just because you have a little bit of a different boundary and grid and all that we already talked about. So just so we all keep consistency, you can base your answers looking at mine. And then we can talk about it as a group afterwards. So I'm going to give you here a few minutes to do that on your side. You're free to talk with others if you wish. But if you want to do it alone, you're also welcome to do that. And while you're doing that, I'm going to set up a quiz that follows this part. So you can get working on that.
Dr. Bastos, I
Yes.
have a question. So my aspect has letter A sharing with both high stable and unstable. My aspect graph has ABC for unstable. How do you want me to define that?
So, Kathy, I guess just so we all are on the same page, I want everyone to answer based on mine.
Okay.
Yeah,
So,
look at
uh,
my feet and then answer based on that.
thank you.
Thanks. Okay, so I think you probably had enough time to complete on our side. So let me ask for a few of you to tell me what you found. So let's see. If somebody can help me here with a couple of them for low stable, what did you find? Okay, so low stable has the lowest elevation, right? All right, so Amandeep, help me with that. Let's go to Tifton. If each one of you can tell me one here. So what about slope? We can start with Marco.
Intermediate,
Intermediate. Polly, what about aspects?
lowest,
Lowest. Uh, Benedetta, what about ECA shallow?
Lowest.
Lowest as well. And what about ECA deep, Luke?
also lowest.
Lowest, right? I think that's what I got on my side as well. And now let's go to the unstable. Yathi, can you tell me elevation?
Intermediate.
Elevation, you got intermediate on unstable. Let me double. I think I had a different one.
Because we have a D which is lowest in elevation.
That is true.
Let's see as intermediate.
Intermediate. What about yellow? Amandeep, let's go back to you again. Lowest. That's what I had as well. What about ECA deep? I think Mohit is on his phone, so I'm gonna get him some slack today. Holy, back to you. What about ECA deep on unstable?
Lowest,
Lowest, that's what I had as well. Marco, what about slope?
intermediate, low.
Intermediate low. Let's just double check here. So slope on unstable, yep, intermediate low, right? Because it's not only C, it has that B as well, meaning that is not different from low stable either. And what about aspect, Benedetta?
Aspect was intermediate.
Intermediate, right? Awesome. Okay, so now what I want to ask you all to do is actually to go to ELC. I have a quiz about that. So my question to you all is, okay, so now we kind of ranked these different variables for these different zones of yield, spatial temporal stability. Now I basically want you to tell me, why do you think that is? So, why do you think that high stable areas are happening under these conditions? And why do you think that low and unstable are happening under those conditions? That's what I'm asking you to do. I'm going to give you here 5 minutes to complete that. And then we'll come back and discuss some of the points that you all made. So let me launch here a timer, and then I'll give you 5 minutes. I think you're already seeing the quiz, right? Luke, can you see as well on your side?
Very yeah.
Okay, perfect. All right, we have about 40 seconds here. All right, our time is up. Make sure to wrap up your answers and submit them. Yeah, there are 3 questions. Yeah, that's okay if you didn't answer the last question. That's okay. Um, yeah, that's all right. You can just submit something. Okay, so I think I have a few answers at this point. Make sure to submit yours. All right, so we're gonna have to move on. And really, there's no right or wrong answer here. It's just I wanted to get to see if you were thinking about this. I'm not gonna be able to read all of your answers because they're more complex, but I guess I'm gonna give you my interpretation, and then you can tell me if you agree or disagree, because these really are just hypotheses, right? I don't have the correct answer, or maybe you're thinking in a way different than mine, and that is totally fine. All right, so I asked you first, let's see here, let me open one of them just to have the questions in front of me. So I asked you, why do you think that the high stable areas were such, right? So we see the high stable, they are sitting higher in the topography, they have higher elevation, but at the same time, they have one of the lowest slopes, right? So they're sitting high on the field, but at a relatively flatter area of the field compared to the rest. The aspect perhaps is a little bit more difficult for us to really explain, because aspect is just the direction of that slope. But then if we come to EC, we see that at a shallow EC, the high stable is intermediary, but towards the higher levels, and it's high on the deep EC. So the way that I would interpret this is basically that it's sitting high on the field, so it's not undergoing as much erosion. And also is sitting on a part of the field that has relatively higher EC, especially at deep layers, meaning that perhaps it has better cation exchange capacity, water holding capacity, maybe just has better soil properties that allow it to be high stable over time. Did anyone think or hypothesize something different that you'd like to share?
Can you say that the stability increase as the elevation increase?
Yeah, for this field, I totally agree, right? So if we look at the elevation map, we definitely see that pulley, right? So the lowest elevations, we have less stability. But then we have the unstable in the low elevation. And that is really interesting to think about. And we're gonna get to that question as well. So the second question here was the same, but on the low stable. Why were low stable areas having these features, right? So we see low stable being lower elevation, so it's sitting at a lower part of the field. It has a relatively high or in intermediate slope, but close, I mean, it's a B and not a C, right? So it has that intermediate slope that perhaps is contributing to some erosion. And then it has both shallow and deep EC low, right? So maybe it's in this part of the field that perhaps some water is draining over, perhaps it has some erosion problems, and at the same time, it has more sand than other parts of the field. And perhaps, it has good drainage potentially, but it also probably doesn't have as good of a cation exchange capacity to hold nutrients and hold water as well, right? Because drainage is good when you have too much water, but a lot of drainage is not good when you are under drought because it means you also don't hold as much water when you need it. Yep.
When elevation and slope, they are slope is intermediate
Mm-hmm.
and elevation is low. So we can say it's like balanced topography.
So so say that again, when the slope is intermediate,
Yeah, slope is intermediate and elevation is low.
is low.
So we can say it's like balanced topography.
Like, you mean like flatter field?
Yeah,
Yeah, I mean, definitely. So the elevation itself, it gives us more information about what, like, if it's at a high point of the field, a intermediate or low point of the field. Just because it's a high or low doesn't mean that's eroding. Of course, if there is erosion, it would happen from high to low elevation, right? But just because it has a differential in elevation does not mean you have erosion necessarily, because then it depends on the slope, right? Because imagine, like, if you have a field that has terraces, right? You have high, medium, and low elevation, but you're controlling for erosion by basically decreasing slope, right? But this field here is not terraced, and so we know that there's these elevation differences are sitting in different levels of altitude of the field, but that there is some slope, right, between them or across them. Yeah, awesome. Thanks, Aman. And then finally here, the question about the unstable. And the unstable is really very interesting to think about, because the unstable areas, it means that they could have been high yielding in some years and could have been low yielding in other years. So the unstable perhaps are the ones that show more interaction with weather, right? Because weather is the key thing that is changing from one year to the next. So if we look here, we see the unstable are also sitting low in the topography, just like, or very similar to the low stable. We see that they have, when it comes to slope, their slope is not different from the high stable or the low stable. So they have similar slopes to both high and low stable. Aspect, again, is a little bit difficult to really make sense of that. And when it comes to electroconductivity, it is both on the shallow and deep is very low compared to the low stable. So really perhaps the main differentiating factor between unstable and low stable in this field is that it has a little bit lower slope than the low stable, because everything else is pretty similar. Sitting at a lower part of the field, it has a little bit of a lower slope, but then EC at both depths is pretty similar. And and potentially those features make it so that in some years where you have more or less rain, the unstable responds differently than the low stable as far as its impact on yield. So those are some of the hypotheses that we could come up with here. And really, it's really interesting to think about the unstable from a management perspective as well, because if you're creating zones of yield potential and stability like we did here, you kind of know what to expect from the high, medium, and low stable. But the unstable, not as much, right? The unstable may be high yielding this year, it may be low yielding this year. It's more uncertain because it's the one that perhaps interact the most with weather. But those were some thoughts I had around this. Anyone has any other thoughts that maybe I didn't cover that you would like to express? All right, so let's keep going. Okay, so with that, we pretty much wrap up this exercise. So here we, again, just as a reminder, we brought all those process layers of yield stability, terrain variables, and soil electric conductivity variables into the same script. We joined all them in one object and then exported that object to file as a single GeoJSON file. And then we validated the stability zones, right? So we were able to perhaps have some intelligence around what are the main factors differentiating these different yield zones. And again, I just want to reinforce the idea that we only, for this field, we only have terrain and soil EC. Perhaps there are other layers that could be even more important here. Perhaps, you know, if we had a compaction layer, if we have a nematode spatial count layer, if we have a pH or soil phosphorus or potassium layers, perhaps those could also help us understand why these zones are different, especially if the main yield limiting factor is related to one of those other zones or one of those other layers, right? So here are just some hypotheses for us to think about and kind of I guess, go through the hypothesis of why these stability zones are what they are. So with that, we wrap up this part of the exercise, and our next step is going to be to create management zones that are going to be based solely on terrain and EC variables. So really, if you think of it, the yield spatial temporal stability zones, you could use them as a management zone if you're managing for something that responds to your potential. Like, for example, nitrogen. And we're going to see this in the future, in a future exercise. However, there are some other variables that we may want to vary inputs, not based on yield necessarily, but perhaps based on soil test levels. So for example, if you are working with variable rate phosphorus, potassium, lime, which is connected to pH, or other nutrients that are more stable in the soil, then we would use soil data layers to create those zones rather than yield data layers in that case. Although in this class, we're not going to really see gridded soil data like pH and phosphorus and potassium to create variable rate prescriptions for that, we will be creating a variable rate prescription for nitrogen, which is a nutrient that is very dynamic once we apply it to the soil, and therefore using soil levels is not really the best way. So we're going to use the yield potential zones that we created in a future exercise to create variable rate application of nitrogen. All right, so again, our next step now is going to be to create management zones based solely on terrain and EC variables, so ignoring yield data at this point. Okay, so make sure you save your script. You can close this RStudio window if you wish. We're not going to be using this project anymore. I shared another file with you on GitHub, and I asked you to create a new exercise called 11 Management Zone. I asked you to create the code data and output subfolders, to move this script I shared with you to the code folder, and then create an RStudio project at that level. I did all that as well before class. I hope you had time to do before class too. And if you didn't, you know the drill. You can catch up with me on your side if you need to. If you were able to create all this, we'll go ahead and launch this RStudio project. And on the Files tab, on the Code subfolder, we'll launch this script as well. Okay, so before I start here, I just want to give another opportunity if anyone has any thoughts or questions about what we did already, or maybe about what we're going to do.
So when our ECA, deeper ECA is higher, and if our shallow ECA is lower, that means still we can say like soil is eroded, like upper than the soil, less water retention.
Okay, so let me repeat that question. So Aman is asking, so if the deep EC is higher and the tops and the shallow EC is lower,
Yeah.
then we can assume it's eroded? Is that
Upper,
the upper? So, yeah, go ahead.
yes.
So it's really, I mean, we know the field is eroded because we've seen satellite imagery from it, but just from EC, you wouldn't be really able to tell, right? Just from the EC itself, because especially in Georgia, fields have a lot of spatial variability in soil texture, especially. So if you go to a field, you're gonna like you can really see, right, that some parts are sandier, some parts are more clay. And so that spatial variability that will be reflected in soil EC is gonna be there regardless if it is eroded or not. I mean, not always, but you know, a lot of fields in Georgia. And so the fact that we have so in some areas we had a lower EC on the shallow and higher EC on the deeper. It just means that we have, so lower on the shallow means we have more sand, or we have coarser texture soils on the shallow, and higher EC on the deeper layers, it means that we have higher EC, we have more either clay or silt compared to sand, right? So it's just a shift in texture pretty much that we're seeing. But that by itself doesn't mean it's eroded. Like we would have to actually go to the field and check it out if that was the case. But that's how I would interpret that. Yeah. Thanks, man. All right, any other questions before we get started? Okay, good deal. So today's exercise, or this exercise, the goal of it is going to be for us to create management zones. And so for that, we're going to have to import that one single layer that we exported on the previous exercise. And then to do the actual management zone creation, we're going to use a clustering algorithm called k-means. There are different algorithms that can be used to create zones. So another popular one is called fuzzy k-means, which is pretty similar in implementation. It's just a different way to assign membership to a cluster. But we're going to be using k-means. It's a pretty common clustering algorithm overall. So that's why I wanted to expose you to that. And then once we create those zones, we're going to assess how the variables are impacting different zones. So once we create the management zones, we're going to do the same box plots and same letters, but now instead of having yield stability classes in the x-axis, we're going to have zone. So zone 1 and 2, or 1, 2, and 3, depending how many we end up creating. And then we're going to explain those zones by using the same variables just to characterize them. So maybe we can say, well, zone 1 has high elevation, high EC, so on. And then we can put a meaning to them. And then finally, we're going to validate our soil-based zones with our yield spatial temporal stability areas and try to understand if there is a relationship there between the zones we're creating based only on soil and the stability areas that we created based only on yields. All right, so I left you here 3 install.packages. As always, I ask you to just remove the comment, run only that line of code, and then comment off again, or just delete that install packages. But I'm asking you here to basically install the Facto Extra package. It's a package that's going to help us to check some of the clustering metrics. The NBClust package, which similarly is going to help us to determine many indices to decide how many clusters we need. And the ggpubr package, which is just going to help us to put some p-values on the plots without having to calculate ourselves. Once you install all of them, you can just go ahead. Well, once you install and you either delete the install.packages or you comment off again, you can go ahead and just run the whole chunk. So you load all the packages. The next step here is going to be for us to import the data that we created on the previous project, right? So that allv.geojson object that we created. So we come here we're gonna use read SF because that was a GeoJSON file. And to navigate there, we need to get outside of code. We need to get outside of this project. We need to go inside of the 10 stability validation project. Go inside of data and bring in the all_v.geojson. If you run that, it pops up on our environment. And then if we can check it, on my side, I have 4,046 rows. You have a different number because again, it comes from the interpolation, which comes from the grid, which comes from the boundary, which each of us have a slightly different version of that. And then it has all those variables. So the standardized yield for 17, 19, 2020, mean pixel, ST pixel, CV pixel, the ST class, elevation, slope, aspect, full direction, and then ECA, shallow and deep. So this was the object that we merged all these layers in the previous exercise. I also want to bring in the boundary so we can always bring the boundary into our plots. Let's do a read SF. We've done this a few times already, so you should be familiar with how to get this, but we need to get all the way out of this project. So .. to get outside code, .. to get outside the project. We go inside 0.5 digitizing. We go inside of data, or I think this case is output actually. We go inside output and it's boundary GeoJSON. We can run that and print it. This is just our boundary. Also, let me make sure that all of our layers are in UTM. So the first one here, the all-v, it is UTM, so we don't have to worry about it. But our boundary is not. Our boundary is WGS84. So we're just gonna transform it. So give it a pipe. We're gonna call ST transform, as you're probably already familiar with the CRS equals to 6345. So that transforms it to UTM zone 16 north. Okay, so as always, even though we have seen this layer over and over again, I just want to get a summary of all V, just to make sure that things make sense. So I'm going to focus here perhaps on the elevation, 45 to 53. We have slope, 0.2 to 7% with an ACE, aspect with some NAs, full direction as well. And then ECA 30 and 90, no NAs. So, we talked already about this, of why we have NAs in slope and aspect, especially. I'm not going to talk again about it just because we already talked about it, but I just want to make sure that you're familiar with the reason why, because that is a good question for something at some point. So just make sure you refer back to that conversation that we had, I think, last class. Okay, so before we actually do the management zones, I want to explain to you what is K-means, how does it work, and how we're going to implement it in R. Somebody has a question?
No, sorry.
Okay, so K-means is a unsupervised clustering algorithm that partitions the data into K groups, where K is basically defined by us, by the user. And it's called K-means because, again, that K is the number of groups, and that's something that is determined, well, it's determined by the data, but we are the ones deciding what is K at the end. I think I have some, let me see here. Let me check my code very quickly. Okay, so we're going to talk about why it's called unsupervised, but I want to make a quick reference here. So if you've been working with anything else that involves model training of some sort, it could be a clustering model like K-means, it could be random forest, it could be XGBoost, it could be anything that would be more like machine learning type of topics. Overall, these algorithms, they have one way of classify all these algorithms is whether the algorithm is supervised or unsupervised. K-means is unsupervised. What does that mean? So basically, an unsupervised algorithm does not have a y variable. You don't say y explained by a lot of x's. You basically say, I have all these x's, these x variables, make groups based on them. So another way of saying this is that k-means as an unsupervised algorithm does not have labels. We're not telling the algorithm, hey, here are high, low, and medium zones. Find patterns to describe these zones. That's not what we're saying. We're saying here's a lot of data. So here's EC, terrain variables, elevation slope, anything else. Here's my data. Find groups in my data. That's what we're telling it. And k-means is going to find groups for you and is going to suggest how many groups it thinks there is in your data. And therefore, once you determine that number of groups, then that's how many groups you have. You give them a label then, once you make sense of them. So let's say in our case, our groups are zones. We're working with management zones. So our group is going to be zones. If k-means tell us there are 2 zones or 2 groups in this data, that's what we're going to go with. And then we're going to try to understand why are they different, which is the validation part of it that comes later. So again, taking a step back here, if you ever ran, perhaps we've worked with random forest, which is a common algorithm these days. If you work with random forest is a supervised algorithm because it needs for you to specify the y variable, the labels. You need to tell it what is the y variable and then explain that y variable with a lot of x variables. A non-supervised algorithm, you do not give a y variable. You only give x variables and asks for it to find groups for you. All right, so I want to show you here if you run this chunk here, it's going to bring a picture, which basically it has, let me see if I can squeeze this in to get everything in one screen. So this plot here basically has 2 dimensions, dimension 1 on the x and dimension 2 on the y. You can really think of these as 2 variables. Maybe dimension 1 could be soil EC shallow, and dimension 2 could be elevation. Just think of them as 2 variables. And then on this picture, we're seeing this kind of plot of the relationship between that x and that y variable. Now, if you were to visually tell me how many groups you think there is in this 2-dimensional data set, how many would you say there is or there are? Okay, I'm going to say 3. Anybody has a different opinion?
Okay, 3 groups.
Did you say 3 as well, Polly?
Yes, 3 groups.
3 groups, right? It looks like 3, right? And just visually, we can assess that it looks like we have 3 groups. So 1 right here, 1 there, and 1 there. Awesome. All right, so if you have a simple data set that only has 1 or 2 x variables, so 1 x variable on the x-axis, the second x variable on the y-axis, you can really visually check, right? It's easy for you to make a plot and look, which is the case that I'm showing in this example above. So if we only had 2 variables and this is the plot that we saw, we could go ahead and run a k-means algorithm with k equals 3. And that would probably be the best choice for k. However, there is a problem that normally we're doing k-means or any clustering algorithm with a lot more than just 2 variables. In our case, I think we're going to use 4 or 5, which is not on the high side yet, but is difficult to visualize 4 to 5 variables in a plot, right? We have a 2-dimensional plot. Perhaps you could do a 3D plot on a computer. I mean, perhaps not. You can do a 3D plot in a computer, but imagine that the more variables you have, each variable adds a dimension. Our brains have a hard time understanding more than 3, maybe 4 dimensions. But beyond that point we cannot make sense of more than that. So it really becomes difficult for humans to make sense when you have a lot of variables and therefore a lot of dimensions. So we need to rely on algorithms to do that for us, to mathematically be able to navigate that multidimensional space and find groupings for us. So if we come back to this example here, I just want to show you how it will look like if we were to set that we have three groups in this case specifically. It would maybe look something like this initially. So the way the k-means work, and I think I have an explanation below here. Yeah. So the way the k-means work, I want to walk you through very slowly to make sure you understand. It is a iterative process. On the first iteration of k-means, it selects three random observations in your data set. So three actual observations. Random. Three random. In this case, three because we're telling k equals 3. So it selects three random observations, which are the ones highlighted with the cross and with the circle around them. So those three observations were randomly selected at the first step. After identifying those three observations, the distance of each one of the points is calculated in relation to each one of those centers. So for example, take this observation here. This observation I'm highlighting, the distance from that one to the center of the red cluster is calculated. The distance of that to the center of the purple center is calculated. And the distance of that to the center of the green cluster is calculated. Whichever is the smallest distance is what is going to be the membership of that point. So here this point is purple because the distance from this point to the center of the purple center is the smallest difference. So that's why this purple in the first iteration became a purple point or became parts of the purple cluster. But this is just the first iteration. So first iteration picks three random observations in the data set, sets them as the center of the clusters, calculate the distance of all points to all the centers, assigns a membership to every point based on the smallest distance to one of the centers. And then at that point, once it has assigned a membership on the first run, it basically recalculates the position of the center of each cluster based on the members that were assigned on that run. I know that just saying words may be a little bit difficult to visualize. We're going to have a better way of visualizing this in practice, but I just want to let you know what you're going to see before you see it, so it's easier for you to identify what's going on, because it's going to go really fast. But so again, first iteration, three random observations. They are set as the center of the clusters. The distance of all observations to those three centers are calculated. The shortest distance to one of the centers is then used to assign a membership to each and every observation. Once that first iteration happens, now everything that was assigned purple in this case is used to calculate the average on the x-axis and on the y-axis. And now the new center of the cluster purple shifts to the middle. And the same happens with the green, the same happens with the red. Once the new centers are shifted, because now they are the average of both x and y coordinates for all data points within the cluster, now the center shifted to the center, and now everything happens again. So all observations, distance from each one of the cluster centers are again calculated. Membership is reassigned based on the closest center to that observation, and then takes the average again, reassigns everything, moves around, reassigns everything, and keeps changing, keeps evolving until the model is able to finalize in a point that the centers are not changing anymore. So you reach a stable state of the model. You basically were able to assign the centers, and now they're not changing anymore because you already optimize the centers this way. So I know that is a lot of conversation. I have all that text explained below here. So if you want to take a look at that again with a little bit more time, you can get back to that. But I want to show here a GIF that's going to really demonstrate that in action. So we have this step here on the top, which is doing what I told you. And you can see that the first, so at step 1, it just randomly selects 3 centers, calculates all distances, assigns membership, recalculate the center, calculates all distances, reassign membership, shift the center again, and does this until enough iterations go by, at which point the centers are not changing anymore. The cluster centers are stable. That's what you see here. So on step 7, 8, 9, you really see big shifts between the centers, and then they stabilize in those centers, and then that is the end of the run. Then it basically has found the center of each one of those 3 clusters. Now we see here that on the first time, the first step here, where it chooses 3 random observations, it could happen by random chance that all 3 observations are really close to each other, and you have issues with really finding the true centers because the initial steps were so close to each other. Imagine that if all 3 data points are really together here in one side of the data frame or the distribution, it could become difficult for the model to iterate until it finds a solution to the problem. And we have a way of avoiding that from happening, which we're going to talk in a second here. But this is basically how k-means works. It basically is a distance-based algorithm that calculates distance from the center of the cluster to each observation, assigns membership, updates the center of the cluster, assigns membership, updates, assign, until it reaches an equilibrium where the centers are not shifting anymore. And then at that point, the algorithm has succeeded and it stops. All right, I know I just told you a lot of things. I hope you're able to get some of that. But if you were not, or if you have some confusion about anything, any questions at this point?
I do have a question. I don't know if we're gonna get to this or if this even makes any sense, but like, okay, so it's obvious in this scenario that there's like 3 groups and you can see how it works like this, but like, could you do this same sort of concept in, like, there's just 2 dimensions here. If we had like a bunch of dimensions and we had the same thing going, could we get like a situation where there's a lot of different steady states that it can reach and a lot of different potential groups? Does that make sense? Like different distributions of these groups?
Yeah.
I don't know how else to phrase that.
Oh, that's a great question. And the answer is yes. So a few different things can happen. So the more variables we have, and therefore the more dimensions, the harder it is for us to really visually check, right? It's going to be hard to say, oh yeah, we have 3 here. Or maybe if we chose 2, and then the centers would be, let's say if we told for it to look for 2 groups, k equals 2, look for 2, it would probably have one of the x's right here and one of the x's right here, I'm guessing. Right? And if you were able to check that visually, in this case, we would clearly see, okay, this is not right. We need 3 clusters here. However, the more dimensions we have, the more difficult it is to visually check, in which case then we have to rely in some other approaches to determine the number of k, the best number of k for a given data set. And we're going to talk about that in a second here. So that perhaps answers the part of like, if we have many more dimensions, how can we know what is the best k? We're going to get to that in the next step here. And the other part that we want to get, that I want to make clear that we all understand, which is also part of the script, is that even though k-means is a very popular algorithm, it's not the silver bullet. It's going to work well in some situations. It's going to fail miserably in others. And I want you all to be aware of that. So we have that understanding that you can always run k-means. It doesn't mean it's going to be the best for a given data set. And we're going to check some examples here to really go through when k-means is not a good option for this. Thanks, Luke. Appreciate the question. All right. So a few properties of k-means. So again, k-means is a clustering algorithm. So it uses to create clusters, to create groups, to create zones when you don't know yet what they are. So remember, we don't have the label, we don't have the y variable, we just have a lot of x variables, and we're asking k-means to look for patterns for us. Again, it is an unsupervised analysis, meaning that if you have a formula of the type y explained by x, k-means does not have a y variable. It only has x variables. So it only has variables to the right side of the equal, to the right side of the equal sign in a formula like this. Another way of saying this is that it only takes predictors or x variables. It does not take a predicted variable, which is the y variable. Also, predictors need to be numerical. So it does not handle categorical predictors. Like in our case, even though flow direction, when we bring into R, it is seen as a double because it's 1, 2, 4, 8. But really, those numbers don't mean anything other than cardinal directions. And because of that, really flow there should be perhaps categorical. Even if we have numbers, we should set as factor. And in that case, k-means does not handle that. So any categorical variable is going to have to be dropped at that point. All right, so we're going to talk about some of the shortcomings of k-means. So k-means is very useful when your clusters are circular and not necessarily in a spatial context, but in a spatial, in a context of the dimensions of your data, right? So here, for example, maybe these points could be coming from a spatial data set. Maybe they all behind the scenes have a longitude and latitude coordinates, but that coordinate is not what I'm showing on X and Y. I'm showing perhaps elevation and you see shallow, right? So when we say that they're circular, it's not that they're circular in space, in a spatial context, is that they're circular in the dimension of the data set that they have, not in a geospatial way, but in a statistical distribution sort of way. So k-means is really useful when they're circular, but can fail very badly if you have odd shapes or outliers. So if your clusters are not circular, and or they have outliers, k-means can fail very miserably because it depends on the distance, and distances are can be impacted by odd shapes and outliers. So if you run the next chunk, I have a figure from a paper that I want to show you here. So what's going on here is that each row of this figure is a different data set. Each column of this figure is a different clustering algorithm. The one that relates to k-means is the first column. So what I want you to show you first is that k-means work the best for this data set, where you have three very distinct circular shapes of clusters. Now, if you take circular clusters, but you increase the variability around them, so there's more overlap between them, k-means does an okay job. It was not the best, but it's not the worst either. But if you have weird shapes, k-means can fail very badly. For example, on this first data set here that you have two circles, ideally, at least intuitively, you would imagine that the inner circle would be a cluster and the outer circle would be a second cluster. K-means does not recognize that. It breaks them right in the middle. However, some other algorithms do recognize them. So for example, spectral clustering is a different algorithm. It did recognize that pretty well. Agglomerative clustering as well, and dbScan as well. Whereas k-means just cut them right through the middle, not a good job. The second example here is also a good example. So you would imagine that perhaps intuitively you would have a cluster that would be the upper semicircle as one cluster and the lower semicircle as another cluster. K-means just cuts them kind of in two. Whereas again, the same algorithms here of spectral clustering, word, agglomerative clustering, DBSCAN do a better job at finding those two clusters. Then we have this other different shape here, which is like 3 elongated clusters. As you can see, k-means, because these shapes are not circular, they're elongated, k-means also does not do a good job in finding the 3 clusters, whereas some other algorithms do a better job, right? So we see perhaps DBSCAN being the better one of all of them. And then we already talked about this, the very nice circular ones. Then lastly, we have this final cluster. So this final cluster is really interesting because, to tell the truth, I don't know what is the correct number of clusters on this last row of example here. But you can see how you get a different answer from different algorithms. So k-means is saying I have 3 clusters. Propagation is saying I have 4. Mean shift is saying I have 1. So you have different answers, right? So with that, I wanted to show you this to give you an idea that k-means is a very popular algorithm, is perhaps the most popular clustering algorithm out there. It's not a silver bullet. It can work pretty well in some occasions. It can fail miserably in others. The tricky part is that you never really, I don't think there is really an easy way for you to know when k-means is working well or not, especially if you have too many dimensions. That is difficult for you to plot all that together. So really what I would recommend is perhaps you run a couple or a few different clustering algorithms and check the results, validate the results, and see which one makes more sense. Perhaps that would be a way for us to really be able to tell here what's the best. Because again, remember that the main idea behind a clustering algorithm is that you don't know how many clusters there is there. You cannot tell if there's 3, there's 4, there's 10. It's up to the algorithm to find how many there are and what are they. So it's difficult because we don't have the ground truth of this. We don't know how many there are there in this case. So it's a little bit trickier to really know for sure if whatever algorithm you're using for clustering is doing a good or a bad job. But at least we should be aware of these types of situations, that k-means is useful, popular, but is not a silver bullet. Okay, any questions about this? Okay, so just a last quick note on this is that perhaps you could use some machine learning techniques like data splitting between training, validation, and test, and then select the model that has the best prediction accuracy. Perhaps you could do something like that to test if k-means is doing a good job or not. We're not going to be doing that in this class. This is something that we do in my other class. But just to let you know that this could be one way that we could use to check how well k-means is performing. All right, putting all that aside, now we're going to look into k-means in practice. So we're going to basically start taking some of the steps to run k-means on our data sets. So some of the prep steps that we need here is, before we run k-means, we need to make sure that our data does not contain NA values. And the reason for that is because k-means does not handle NA values. If you have even a single NA cell in an entire data set that you give to k-means, it's going to throw you an error. It's going to say does not know how to handle that. So we need to first remove NA values. As we already talked about before, k-means only works on numerical variables. So we're going to have to keep only numerical outcomes. We cannot give it a categorical outcome. So we're going to do that. And also, we're going to standardize our variables. What do I mean by that? So if we run a summary here just to look into it, the variables we're going to give it are going to be, we're not going to give all these variables. We're just going to give the most important ones to k-means that are related to soil. But if you look into it, for example, let's compare here. Okay, so maybe comparing aspect to slope. Maybe that's a good comparison. if we do not standardize our variables, and what I mean by standardize is make them to have the same range of values. So maybe ranging from 0 to 1, or maybe being centered around 0 and then ranging from perhaps -1 to 1, or some way of standardizing the variables. If we do not do that before we run k-means, what could happen is that variables that have inherently larger magnitude will have a larger impact in the model. Not because they're more important, but just because they have a larger magnitude. So for example, if we were to include aspect in our analysis, aspect ranges from 0 to 360, whereas slope ranges from 0 to 7. You can clearly see that there's at least a 10-fold difference in magnitude between aspect and slope. If we don't standardize the variables before giving to k-means, perhaps aspect is going to be the most important variable. Not because it is the most important variable itself, but because it has the largest magnitude of values. It has the larger numerical value. And we want to avoid that. We don't want that to be the main factor deriving or saying if the variable is important or not. So we want the actual variability within the variable to be the driving force. And so we're going to have to standardize these columns as well. All right, so if you come to the next chunk, this is where we're going to create the object. We're going to prepare the object to run k-means. So if you go there, I'm going to assign the results to this object called all_vn. I'm going to give it the assignment symbol. We're going to start with all_v. Give it a pipe and then come to the next, after the next comment here. So to drop all NA cells, regardless of which column they are. So let's say if we have one column that has one cell of NA, that cell, the whole row is going to be removed, not just that cell. So let's say you have one NA in slope, which we know we have NAs in slope and aspect, but all the other cells for the other variables are not NAs, right? They have values in those cells. But because this cell of slope has an NA, the whole row is dropped. That's what we want to do. So just so it makes sense here, all V has on my side at least, 4,046 rows. We're going to apply the function drop NA. So if you go ahead and run this, and now you print all VN, on my side, I lost about 300 rows. So now I went from 4,000 something to 3,723. That's because any row that had at least one NA in that row, the whole row was dropped. So we do not have NAs. All right, first step accomplished. Now the next step, I want to only select the variables of interest. So remember that those are going to be variables that are soil related because we want to do the soil-based management zones. And we're going to only keep numerical ones. So add a pipe here. Come after that next comment. Let's use here a dplyr select to only select some variables. So all the standardized yield variables, again, I don't care for them at this point because we are going to do management zones based on soil variables only. So the soil variables start on 11M. So we're going to basically say here that starting on 11M colon, and then if you come all the way to the end of this data set, the last soil variable is ECA 90 DSM. So from 11M to ECA 90 DSM, if you run that, you end up now with 7 columns: elevation, slope, aspect, flow direction, ECA 30 and ECA 90 in the geometry. What I want to do here actually is I want to leave behind flow direction because it is seen as numerical, but it's really categorical, right? These numbers do not represent, it does not mean that 2 is twice as much as 1. It just means that 1 is north, 2 is northeast, right? So I want to, on the select, I want to come here and say minus flow dir. And I also want to remove aspect, because I think aspect, although it could be useful to perhaps understand the direction, but the way that we represent it in degrees is perhaps not the clear for us to make sense of it. So I just want to remove aspect as well. If you run this and you print all VN, now we have 5 columns: elevation, slope, ECA 30, ECA 90, and geometry. We're going to talk about the geometry later because we cannot have geometry when we do the k-means, but we're going to keep it here for now just so we have that spatial context. Because remember, in the end, we will need to plot these. We want to make a map of these zones. So we need to know where in space those cells are. And then here's what we're going to do. We're going to basically standardize each one of these columns using a function called scale. So before we do it, I want to just get help of scale, just so you see what that does. So the function scale is going to scale and center objects. So the default here is center equals true, scale equals true. So center is basically going to divide the values by the average of the column, and scale is going to basically, well, it does the value minus the average divided by the standard deviation. I think that's what both center and scale are doing for us. So if we come here back to the code, you can give a pipe, you come after that standardizing comment. We're going to use a mutate. And here's what we're going to do. We're going to use a function that perhaps you are not as used to using. Every time you want to apply a given function to many columns, we can use the function called across. So across, then we need to specify which columns. One way to say which columns is we could say only the numerical columns. In this case here is going to be everything except geometry. The way that we can say only numerical columns in code is to use the function where and then say is.numeric inside of it. And then close parentheses of that where. So this here is basically saying whichever column is numeric, select them to do what we're going to do next. And what we're going to do next, we give the comma, and then we say the function that we want to apply. So we want to apply the function scale. We're going to give a tilde here and say scale.x. So let me perhaps help you to interpret what this code is doing. So it's basically saying across every column that is numeric, apply the function scale to that column. This is what this code is saying. So before we run it, notice that right now, elevation, slope, ECA, deep and shallow, they are all in their own units, right? So meter for elevation, degree for slope, and then decisiemens per meter for EC columns. Once we run this, and you can go ahead and run it, now their values changed. They changed to be scaled. So now they are centered around 0 with a standard deviation of 1. So I don't think I have the code here, but we can just check a summary. So now if you check the summary of all VN, notice that for all of them, the mean now is 0 because it's being mean centered. And the standard deviation and the minimum and maximum values are just according to that standard deviation of each one of those columns. So now you can see that these variables, they're going to have the same impact on the clustering algorithm because their magnitude is not playing a role here. Okay, I think I went a little bit past our break time, so I want to give you a quick 5-minute break at this point, and then when we come back, we're going to start running k-means and playing around with it a little bit. So let me give you a 5-minute break here, and then when we come back, we start with k-means on our data sets. All right, so let's resume here our exercise. Okay, so we on k-means itself, on the function k-means, we need to tell it what is the k that we want. And so to begin with, let's try 4. So on this next chunk here, give it the assignment symbol. We're going to use a function called k-means from the stats package. We're going to give it our data frame, which is the one that we just created above, all vn. But remember that this data frame still has the geometry. So I want to remove the geometry at this level here. So without saving that on the actual data frame, without saving the fact that we're removing the geometry, but I do not want to give the geometry to k-means. So we can do that kind of on the fly here. So if you give give it a pipe, there is a function called stDropGeometry. So if you just run all v stDropGeometry to see what that does, it basically makes that into a data frame, into a tibble. It drops the geometry because all vn is an SF object. But all vn stDropGeometry, you basically drop the geometry, so it becomes a tibble. And now there are a couple of arguments after that I want to change. The first one is called centers. So centers is basically the number of k, the number of groups you want to try. Let's try 4 first. And then it has another argument here that is called nStart. So nStart, I want to set it to 10, and I want to tell you what this is. nStart is basically how many times the full algorithm of k-means is going to run before it gives you an answer. And I don't mean that's going to do 10 in this case. It does not mean it's going to do 10 iterations. It means that it's going to do the first run, how many iterations it takes to find the center of the clusters. That's one run. And then they're going to do another one and another one, 10 times in this case. And the reason for that goes back to Luke's question. What if you just do one run with all the iterations within that run? And maybe you were just unlucky that your starting centers, which remember, the starting point of k-means, it picks, in this case here, 4 random observations of your data set to be the starting center of the clusters. If by random chance the selection of those 4 observations skew your distribution in some way, and it becomes difficult for the algorithm to navigate the data space and find the centers, the actual final centers, and you just ran once, maybe your answer is going to be different if you're compared to if you run the algorithm another time. So we're asking here to do 10 full runs, where each run, it does all the iterations and finds the centers. And then does another one, all iterations, finds the centers. And then another one, and then 10. And then gives you the results, like an average result across all 10, to make sure that we are not suffering from unlucky of which initial observations are randomly selected to be the centers in the first step. All right, so if you run that, let's print. So it runs very quickly, as you saw. And then if we just print that object, it has a few different things for us to inspect. It's a different way of looking at it. So it's saying that k-means clustering with 4 clusters, and then it gives us how many observations of our total data set was classified in each one of those clusters. And then it gives us here the mean of the clusters for each variable. So here we see, for example, that the cluster number 1 is at an average value of elevation of 0.54, slope minus 36, ECA shallow minus 0.5, and ECA deep of 0.17. Remember that these values are standardized, so they are not on the actual measure units of these columns. They are standardized values, so maybe that's why they're not making a lot of sense as we read them. But then it gives the center for each one of the 4 clusters that we asked for it to create. And then it gives us a clustering vector. So this may not be the best way of showing this, but you can really see that it has a number of observation on top. So we're starting on 1 and going all the way to 4,000. It cuts out at 1,000 actually, but it has 4,000 in some. But then each observation is basically assigned to one of the clusters, right? So we see observation number 1 fell in cluster 3. Observation 2 fell cluster 3. Observation 3 was in cluster 1, and so on. So each one of our observations now have a new column that identifies which cluster they belong to. And then if we just keep scrolling, there's going to be the within cluster sum of squares by cluster, which is basically what we're seeing here. This is the within cluster sum of squares. And then there's the between cluster sum of squares divided by the total sum of squares, representing 60.8% of the variability. All right, so what we want to do is we want to see little sum of squares inside of the cluster. So let's say I want the cluster to not have a lot of variability. I want it to be compact, right? I want those points to be very compact, but I want the variability between clusters to be high. So cluster number 1 here on my left, cluster number 2 on my right. They're both compact, but they're really far from each other. So the variability inside of them is small, but the variability across them is large. That's what would be a good way for us to determine if our clustering has been good or not. Now, so remember here our between by total sum of squares with 4 clusters being 60.8%. Okay, just remember that number, 61. We can think of 61 just to make it easy to memorize. Let's go back to the code here and change our centers to 3. So k equals 3. Let's run that. So this is a k-means with 3 clusters now. Let's print again mod km. And let's go all the way down to check what is our ratio now. So the between sum of the squares by total with 3 clusters decreased to 55%. Okay, so we decrease 1 cluster, the amount that is being explained across clusters decreased. We want this number to actually increase. All right, so what happens then if we increase the number of clusters? So we started with 4, we tested 3, so we went down. Now let's go up, but let's go up by a lot more. So instead of going to 5, let's put 10. 10 clusters. And let's see how that impacts our between divided by total sum of the squares. So it went up to almost 78%. Right? So that is a good thing. But the problem is, so the thing is, the more clusters you have, the more variability you're going to explain. If you think about it, the 2 extremes here is k equals 1, meaning that everything is 1 cluster. There's no difference between clusters. So k equals 1 is the minimum, and the maximum is the number of observations, where each observation is its own cluster, which is also not helpful, right? So k equals 1 is not helpful. K equals 4,060 something is not helpful. What is the number that we need? How do we determine what's the best number of k? Well, there is a way for that. There's a few different ways to determine the best, or maybe more than a few, but we're going to be focusing on a few of them on how to determine the best k for our data set. And I guess part of this conversation as well is the higher is the k, the more variability you're going to explain, which is good in a way that you're explaining more variability. However, imagine you get to a grower and tell them that in this field they have 4,000 zones. I mean, that will never happen. That is ridiculous. but that it would be the extreme of this example, right? So perhaps bringing that to a more applicable conversation. If I tell that grower that they have 10 zones, but really they could get away with 3 only, which one do you think a grower would prefer? It's a lot easier to manage 3 things differently than 10 things differently, right? So if there's not a lot of difference between 3 and 10, you should choose 3. You should choose the simplest model that gets you the most return, or in this case, the simplest. Sorry, not sure what that was, but the simplest model that can help you with the minimum complexity, that still gets you the overall differences in the field, but without getting more complex than necessary, right? So this is our goal here, is to find the best number of K for this data set in specific. Okay, so we just tried K. Now for our data, we tried K3, we tried K4, we tried K10. But that was kind of arbitrary from my side, right? So we did not plot our data like the example that I showed in the beginning, right? That example is not our data, that's something else. So we did not plot it. We don't have a visual idea of how many clusters or how many zones our data should have. So determining 3 or 4 is perhaps subjective and arbitrary. We want to have an objective way of making this decision. There are going to be different tests and metrics that we can use to determine the number of K. All of them are basically going to run the following way. They're going to run a model with K equals 1, extract some metric from that model, and store it in a data frame. They're going to run K equals 2, extract some metrics, and save them. K equals 3, extract metrics, save it, until whatever number of K you determine. Normally, I do 1 to 10. That's normally a range of clusters that I'm interested. Even if a field tell me that, maybe 15 or 20 clusters would be the best, it's very unlikely you're gonna convince a grower to manage something that has 15 or 20 different rates in their field. So I run between 1 and 10 with a preference perhaps to lower values if possible. And then it's going to run all these models with K starting in 1 until K goes to 10. And it's going to extract a metric from that. So it could be that between divided by total sum of squares. And then try to understand how much we're gaining as far as how much more variability we're explaining by each extra cluster. Because there's going to be a point that in the beginning, adding a cluster is going to explain a lot of information. But then after a certain point, adding another cluster is going to explain just a little bit more and not too much more. And then that's the point of marginal returns. That's the point that we want to say, okay, I'm not going beyond this point, because by adding more clusters, I'm just explaining very little more of variability. So let's do that using one of the metrics here, which is the within sum of the squares method. We're going to use here a function from the Facto Extra package. The function name is fvis underscore nbclust. You can read the documentation of this function if you wish. There is a whole vignette of this package that's really great for clustering. So I refer you to that. But on this function here, what it takes is first the data set that we're clustering. That is the all v underscore n. But don't forget to drop geometry. So st drop geometry. Then it has an argument for method. We're going to say method equals to WSS, which stands for the within sum of the squares method. It has another argument for k.max. So this is the maximum number of k you want this algorithm to run the check for you. Again, you can give whatever number you want. I want to give it 10. So it's going to go from 1 to 10 clusters. And then it has this argument for fun cluster, which means the function that is going to apply to create the clusters, which you just say k-means. So once you have this, You can go ahead and run it. It may take just a quick moment here for it to go through because remember, it's running many models from K to 1 until 10. And then it gives you this, this plot here. So let's walk through what this plot is showing. It's showing here number of clusters on the x-axis and the total within sum of the square of your clusters. What we want to have here, so we want to have a low total sum of the squares, but notice that there is a point after which your gains are very small by adding an extra cluster. This is also called the elbow method. And it's the elbow method because it looks like an elbow, right? It looks like this, I guess. Where the goal here is to find the elbow and determine that as the optimal number of clusters. For some data sets, that elbow is very clear. It's almost like a breakpoint. For our data, it's not as clear, and I think for a lot of times it's not as clear. But if you were to say, based on our data, and imagining again that we're looking for the lowest number of clusters that explain a good amount of information. So a balance between number of clusters and amount of variability explained. What would be a number cluster that you think would make sense? Where do you see kind of the break of the elbow in this plot? Okay, I'm on deep set 3. Any other different thoughts?
It's between 2 and 3.
Between 2 and 3?
Mhm.
Yeah. I would say anywhere between maybe 2 and 4 or 2 and 5 would make sense, right? It would be defendable. But definitely, like if we want to try to stay within the smaller number of clusters, I would also agree that 2 to 3 is probably a good answer. All right, so this is one of the methods. It's called the within sum of the squares or the elbow method of determining the number of clusters that we need. I want to now check. Yes, you have a.
So, you said we need less than sum of squares.
In this case, here's the total sum of the squares, so we want to decrease that number. Yeah.
Yeah, so if we have total sum of squares, then we have no percentage of variability.
So the total within sum of the squares, what this is doing is basically, so imagine that if you have, so imagine like, let's go back to the example where we had a plot to think about it. And maybe let's look into this. No, maybe this is better. So right here, if you put 1, right? Imagine that that 1 is probably the center. If we have k equals 1, the center is probably going to be somewhere around here, I'm guessing. And then everything is going to be with the same color, right? So imagine if the center is here, imagine all the variability you have across all this one big cluster, right? But now you change this to 2. So now 2, it may be that you have a cluster center around here and then a center around here. You have less within sum of the squares. So within sum of the squares is how much variability you have in the cluster. So if you have 2 clusters here, you're going to have less variability, less sum of the squares compared to 1. But there is still a lot of noise, right? Because if the center is here, and imagine that you cut right through this cluster, and that would be like to the right is 1, to the left is another 1. You still have a lot of variability for centers here and here, right? But now if you add 3, now you have your centers like we know how this looks like. So it would be a center on each one of these clusters. So now the within sum of the squares has decreased because you have the appropriate number of centers to determine or to characterize the 3 clusters that there are in this figure. So 3 would be perhaps where in this case here, if we were doing 1, 2, 3, it would be very clear that like 1, 2, 3, and then you see an elbow. Because after 3, if you keep adding centers here, imagine that now you would still have, maybe you would still have a center here, but maybe now this big one would be split. So you have a center up here and a center down here. So you are further decreasing how much variability each cluster has, but then you start gaining very little from it. You know, so going from one big cluster with the center right in the middle has the most within variability. Having the 3 is the optimal because it's really representing your data. Having more than 3, so 4, 5, 10, is gonna be explaining some variability, but very little at this point. It's just being nitpicking, kind of. You know, does that make sense? Awesome. Okay, let me go back to our code. Any other questions? Okay, so the next metric we're going to use here is called silhouette width, which the only difference from the previous code is that now we change the method. So the data is the same, Kmax is the same, the fun cluster is the same. It's just the method now is S. And if you look for help of the fvis mbclust function, you're going to be able to see on the documentation what are the methods available and which ones we can use. So here S stands for silhouette width. If we run this, we see that the silhouette width method is basically proposing for us that the best number of clusters is 2, is giving us an objective. It's a different way of looking into this, but that it's giving us an objective recommendation of 2 clusters. So the silhouette width, it's almost like a density plot that it just, as you keep adding clusters, you keep adding density plots specific to those clusters, and is looking at the width of that silhouette overall. I now thinking in retrospect, I wish I had a better visual to show you that. But basically, it's another method here that's looking to a slightly different metric. That's the silhouette width of the clusters. And in this case, is giving us a recommendation of 3 clusters. Oh, sorry, of 2 clusters. Okay, so we just checked 2 metrics. So the within sum of the squares, or the elbow method, and the average silhouette width method. What if different methods give you a different answer? What would you do? And that's very common and very likely to happen. One way to overcome that is to run many metrics and just let them vote. Each metric is going to give you a recommendation. You just choose the number of K that had the most votes, the most recommended number of K across different metrics. I have a note here saying, do not run this code in class because it's going to take a while. And the reason why this takes a while is because it's going to run 26 different metrics. So we just saw 2 metrics. It's going to run 26 different metrics and give you a recommendation to how many clusters you should have. On this code, I'm given the same data. I'm saying that my distance is the Euclidean distance, so it's like a linear distance. I'm saying methods is k-means. I want all the indices, all the 26 indices. And I'm starting with the minimum number of clusters of 2 and the maximum of 6. Instead of 10, I changed to 6 just to go a little bit faster. If you run this in class, it's going to take a while to run, and it may freeze your RStudio for some time while it's running. I don't want you to do that, so you can keep coding in class. But if you want to run this at home to verify on your side, you're welcome to do that. So you can, we can hit run on the chunk and go for a break if you wish. But if you do want to run this at home, please do so. But at least the last time I ran on my side, I had, so of 26 indices that it tests, 13 of them, so half of them, the majority, propose 2 as the best number of clusters. And that's what we're gonna use to continue here. If you are doing something like this in a paper where you have to explain what you're doing in every single step on your methods, you can say that you use this function from this package, which runs 26 indices, and that you chose whatever number of K because that was the majority votes across 26 indices. you can explain something like that. So it's a little bit more objective. Like you were saying, I did not, because imagine if we look at the elbow method at the within some of the squares, maybe you would have said, let's go with 3, or maybe let's go with 4. If you look on the average silhouette, it would say you should go with 2. Now, what do you do, right? You're not sure. So for you to get a more objective decision, you can run all these 26 indices and get the recommendation of the majority vote. Which if you do run at home, or at least when I last ran with my data, I got 2 as the most voted number of clusters. Okay, so now that we determined the number of clusters, this data set that we have here has 2 groups, and that's what we're going to continue with. Let's go ahead and run that final model so we can keep using it. So we're just basically going to come here on this mod KM2, give it the assignment symbol. We're going to call the function k-means again. We're the same way we're going to give all vn and then give the pipe and ask for st drop geometry. So we do not have the geometry. We're going to say centers equals to 2, and the same as before, and start equals to 10. So if you run this, we assign this to the object mod km2. If you printed, this is our object. We have 2 clusters, k equals 2. So with this, we just finished creating our zones. That's it. You just did management zone creation right here. The next step is going to be, of course, to make a lot of plots. So we understand what are these zones, how are they impacted by different variables, and so on. That's going to be the topic of next Tuesday. So make sure you save here your script. I want to open here for you to claim your attendance. So I just opened there. Make sure you claim your attendance. And if you have any questions, we have a few minutes here before the end of class. But if you do not have questions and you claim your attendance, then you're good to go. Thanks, Niva.